Okay, we've built a model. How do we know whether the model is fair? One challenge is that there is no one standard definition of fairness, whether decisions are made by humans or by machines. Both in law and in philosophy, this is a question that engenders lots of debate. This is because defining fairness is difficult. Let's look at our loan example. Imagine that we have two groups of people, blue people and orange people. We're interested in making small loans subject to the following rules. A successful loan makes us a profit of $300 per loan, and an unsuccessful loan costs us a loss of $700 per loan. And everyone has a credit score between 0 and 100. Blue and orange have different distributions of how they will be able to pay back loans, and it might not be fair to ignore them. For example, in the US, black and white people may have different rates of loan payback due to wealth inequality, which is a result of historical discrimination. Or in the insurance field, women tend to live longer than men. So does it make sense to consider insurance rates and policies in the same way? So text in green are correct decisions, and text in red are wrong decisions. The light gray people are those who are denied loans and would default anyhow. The dark gray are those who are denied loans, but they wouldn't default. The light blue and orange are those granted loans, but they default. And the dark blue and the orange are those to whom we give a loan and they pay it back. So let's start off with a naive case where we don't consider any fairness constraints and we're angling solely for profit maximization. There are no constraints here. We are just trying to get the most profit. But the two groups have different thresholds, which means they're held to different standards. In this case, the blue group is at a disadvantage and is held to a higher standard, so many people who could pay back loans are denied loans. Let's consider one fairness definition. We might decide that we want to be completely unaware of which group people belong to, whether they're blue or orange. So here, the blue and the orange thresholds, they're the same. Now, the blue group is being given more loans overall, but the orange group has been given fewer loans. And if you look among the people who would pay back the loan, the orange group is at a disadvantage. That's because it ignores real differences between the two groups. Let's consider a different fairness definition. We might decide to have demographic parity. We want to issue the same fractions of blue and orange loans. The number of loans given to each group is the same, but among the people who would pay back a loan, the blue group is at a disadvantage. That's because a model only looks at loans given, not rates at which loans are paid back. This results in fewer qualified people in the blue group being given loans compared to the orange group. So here's a third fairness definition: equal opportunity. Same fractions of blue and orange loans to people who can pay them off. Among people who would pay back a loan, blue and orange groups do equally well. This choice is almost as profitable as demographic parity, and about as many people get loans overall. The constraint is that the people who can pay back a loan, the same fraction in each group, should actually be given a loan. To recap, the group unaware constraint holds that the thresholds are the same. The demographic parity constraint requires that the same percentage within each subgroup will receive the loan, and the equal opportunity constraint requires that the same fraction within each subgroup who can pay them off will receive the loan. Now, none of these definitions is necessarily better than the other. Each of them has different mathematical properties, and you cannot satisfy them all at the same time. And which constraint you choose depends a lot on the context of the machine learning use case. But you've got to choose.